Welcome to this explainer. Okay, so today we're exploring something that is, honestly, completely mind-bending. The exact same physics laws that govern a massive airplane soaring through the sky, yeah, they're the exact same laws responsible for the curve of a soccer ball and even the blood flowing through your own veins. But as you'll see, behind these everyday miracles lies one of the absolute greatest unsolved mysteries in mathematics. Let's dive in. So, have you ever wondered how blowing air horizontally across a tube can somehow pull liquid vertically right up against gravity? Or how a jet of air can keep a ping pong ball perfectly levitating in midair, literally suspending it without it falling? Well, we're going to figure out the physical cheat codes that make these crazy phenomena happen. Okay, let's lay out our agenda. 1. The magic of Bernoulli. 2. Aerodynamics of unpowered flight. 3. The Magnus effect. And 4. Real fluids and friction. Section 1. The magic of Bernoulli. Now, this equation might look a bit intimidating at first glance, but it's actually just a really beautiful expression of the conservation of energy. Daniel Bernoulli figured out over 200 years ago that for an ideal fluid, if you add up the static pressure, the hydrostatic pressure, and the hydrodynamic pressure, which, by the way, is tied to velocity, that total sum always remains constant. The absolute crucial takeaway here, if a fluid's velocity goes up, its internal pressure absolutely must go down to keep the whole equation balanced. It's a fundamental trade-off. And you can see this trade-off perfectly in something as simple as a spray bottle. If you just blow air freely and, slightly above a vertical tube sitting in water, nothing really happens. But if you configure that horizontal tube so it blows directly across and partially blocks the top of the vertical tube, the air is suddenly forced to speed up. That spike in velocity creates a pressure drop that is actually lower than the atmospheric pressure pushing down on the water in the glass. And the result? The atmosphere literally shoves the water right up the tube, creating a spray. It's amazing. We see the exact same thing with a Bernoulli levitator. So when a high-speed jet of air shoots over a ping pong ball, it creates a low-pressure zone. Think of it like an invisible wall. If the ball starts to drift out of that fast stream, the higher atmospheric pressure surrounding it instantly shoves the ball right back into that low-pressure pocket. I mean, it looks like magic, but it is just pure, balanced math. Section 2. Aerodynamics of unpowered flight. So taking this up a notch, how do these exact same pressure differentials allow a glider weighing hundreds of pounds to fly without an engine? Well, lift isn't just one concept, it's really a team effort. You've got Newton's third law, meaning the wing deflects air downward, which pushes the wing upward. But because of the wing's shape, Bernoulli's principle also kicks in. The air moves faster over the top, creating a low-pressure zone that quite literally sucks the glider upward. And here's a crazy stat. Because velocity is squared in the lift formula, if a glider just doubles its speed, it instantly quadruples its lift. No way, right? But it's true. Now, any aircraft is constantly fighting this tug-of-war between four fundamental forces: lift, pulling up, weight, pulling down, thrust, pushing forward, and drag, pulling back. But wait a second, we're talking about unpowered gliders here. So where on earth does the thrust come from if there's literally no engine? Well, this is where it gets super fascinating. In an unpowered glider, gravity is actually the external engine. The weight vector pulls straight down toward the center of the Earth. But because the glider is on a descending flight path, that weight resolves into two separate components. One perfectly opposes the lift, while the forward component of the weight literally pulls the glider forward, perfectly balancing the drag. So it's converting potential energy, its altitude, directly into the kinetic energy of forward motion. To manage this incredibly delicate balance, a pilot controls the angle of attack. Simply put, this is the angle between the wing and the oncoming air. Increasing this angle linearly increases your coefficient of lift. But, and this is a really big but, if you push that angle past a critical point, you completely disturb that smooth Bernoulli airflow over the top of the wing. The pressure drops disappear, your drag skyrockets, and bam, you experience a stall. Section 3. The Magnus effect. Okay, so what happens if we take these aerodynamic principles and apply them to a rotating object instead of a static wing? Well, this creates something called the Magnus effect. When a sphere or a cylinder rotates in a moving fluid, it actually drags some of that fluid with it, creating a vortex. On one side of the object, the spin is moving in the exact same direction as the oncoming air, which speeds the flow up. But on the opposite side, it spins against the air, slowing it down. And just like our glider wing, this difference in velocity creates a massive pressure drop, generating a really powerful perpendicular force that pushes the object sideways. The real-world applications of this are just incredible. Every single time you see a soccer player bend a dry leaf kick around a wall of defenders, or a tennis player use topspin to drop a shot perfectly in bounds, they are relying on the Magnus effect. Airsoft guns even use hop-up systems that put backspin on tiny plastic pellets to generate lift and drastically extend their range. But we can scale this way, way up, too. Massive modern cargo ships, like the E-Ship 1 and the Viking Grace, they actually use giant spinning cylinders called Flettner rotors as turbo sails. They harness the wind to generate forward thrust, slashing their fuel consumption. It's literally the same physics as a curving soccer ball. Section 4. Real fluids and friction. Now, everything we've discussed so far assumes we're dealing with ideal fluids. But what about the messy reality of fluids traveling through enclosed pipes? Well, first we have to understand the continuity equation. This dictates that in a closed tube, flow rate is constant. Basically, if a pipe narrows, the fluid inside absolutely must speed up. Engineers use something called the Reynolds number to predict if this flow will be smooth and laminar or chaotic and turbulent, which, as you might guess, completely changes how the fluid behaves. And here is the crucial distinction from our ideal math. Real fluids have internal friction. Layers literally rub against each other and the tube walls, which loses energy and causes static pressure to drop. But importantly, not all fluids are equal. Water is a Newtonian fluid, meaning its viscosity stays constant regardless of how it flows. Blood, however, is non-Newtonian. Its viscosity actually changes depending on how fast it's flowing. That makes its behavior inside our bodies incredibly complex. This energy loss to friction is known in hydraulic engineering as head loss. Because blood is a complex, non-Newtonian fluid, this friction is substantial. I mean, even in a perfectly straight vessel, the pressure at the end is always lower than at the beginning. This hemodynamic reality perfectly explains why your heart has to act as such a powerful, continuous pump just to overcome the endless pressure drops happening inside your miles and miles of blood vessels. So we've journeyed from a simple spray bottle on a desk to gliders soaring through the clouds to massive cargo ships on the oceans, all the way down to the blood pumping in your own veins. But here is the mind-bending conclusion to all of this. While we observe and use these laws every single day, we still don't fully understand them mathematically. The Navier-Stokes equations that govern this fluid flow are so ridiculously complex that solving them is literally a $1 million millennium prize problem. Even Kolmogov's mathematical theories on turbulent flow remain incomplete to this day. We rely on this physics to fly, to ship our goods, and literally to stay alive. Yet its deepest mathematical secrets remain completely unsolved. So what other invisible, unsolved forces are silently shaping your world? Keep questioning, and thanks for exploring with us.